So this section, 6-3, is proving that a quadrilateral is a parallelogram. We're on page 321. So last section we talked about the properties of parallelograms. So today we're going to sort of use the converse of those properties and see if a quadrilateral is a parallelogram. And to do this, we're going to decide using several theorems that are converses of the ones from the earlier sections, 6.1, 6.2, and 6.3. Do you remember what converse means? It's when we take what and switch it with what. Converse of a conditional is when we take the hypothesis and switch it with the conclusion. So if you remember, theorem 6.1 stated that the opposite sides of a parallelogram are congruent. So the converse is theorem 6.5, and it states if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So my question to you is, which one of these quadrilaterals is a parallelogram? Is it behind door number 1 or door number 2? Well, you're right. It is the quadrilateral on the left. This is a parallelogram. Okay, theorem 6.2 from the previous section states that opposite angles of parallelograms are congruent. Converse to this is theorem 6.6. So it states that if both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Is this a parallelogram? Yes or no? Yes. Both pairs of opposite angles are congruent. Next is theorem 6.3 from earlier, and it states that the diagonals of a parallelogram bisect each other. So theorem converse, which is going to be theorem 6-7. Everybody want to try to do this? Follows a pattern. If the diagonals of a quadrilateral bisect each other, and the quadrilateral is a parallelogram. Is this figure ABCD parallelogram? Yes. Based on the fact that the only information we've been given is the length of these diagonals, and each side is congruent to the other, this is a quadrilateral.